In this video, we're going to be talking about the limit definition of a derivative, and we're also going to be solving some problems related to the limit definition of a derivative. So at the beginning of the video, right now, I'm going to tell you the plan so you can skip ahead on the timestamps if you want, but I'm going to be explaining where the limit definition of a derivative comes from. So the limit definition of a derivative, usually people use h, is f of x plus h minus f of x over h. I'll show you how people actually came up with this, and trust me, you don't have to do any complicated math. You just need to understand the algebra. But if you don't care, you just want to solve some problems, I have problems at the timestamps of this video. So go ahead and skip if you want, you math degenerates. But let's go first explain your limit definition of the derivative. So let's say there are 2 points with each other, next to each other, correct? And you can define these 2 points as your x, f of x. So f of x is equal to your y value, correct? Your function solves for your y value of your function. And your f of x is your function of x for y. So both of these are equivalent. So x, y makes sense. Now, let's describe the distance between these 2 points as h. So the x distance between these 2 points is h. Not the actual literal distance, but just the distance between the 2 x values. If we describe the distance between the 2 x values as h, we can represent the second point as x plus h, right? If we just add on the length of h here, then we can kind of, on x, then we can kind of just get this x value to the right. Now that we changed our input, since this is our input, the left side is the input of your coordinate piece, we can represent your function, new function, as f of x plus h. And remember, f is just a function of y. So we can kind of say that this is x1, and this is y1, and your x plus h is x2 and y2, different coordinate pairs. So remember how to calculate slope. You can calculate slope by subtracting, let's not do subtraction first. Let's do change in y over change in x. Well, we can subtract y2 minus y1 over x2 minus x1. All right, the coordinate pair is subtracted from each other. So now that we have this, well, what is y2? Well, y2 to us is f of x plus h, and y1 is f of x, your function. And what is x2? Well, x2 is x plus h, and x1 is just x. So we subtract x from here. But the x's cancel out right here. Positive x minus x is just nothing, 0. So we can cancel out the x values, and we just get left off with h. Now we're getting awfully close to your limit definition of a derivative. Well, what if our h value got smaller? What if we made the h value maybe half the length? No, what if we made it even smaller? So this point gets dragged closer. All right, now the x2 and y2 are right here. Well, what if we drag it even smaller? What if we make the h value even smaller, the distance between the 2 points even smaller? Small enough to be the limit as h approaches 0. Well, now we have the limit definition of a derivative. These two, I wrote the same exact thing. So I'll actually show you right now how to solve for your functions using the limit definition of a derivative. For this problem, we need to solve for our derivative at point 24 on the graph x squared. So let's use our limit definition of a derivative. Well, the limit definition of derivative is as h approaches 0 for f of x plus h minus f of x over h. So what is f of x in this case? Well, f of x is our function that we want to solve for, which is x squared. And h is approaching 0. So we can't just directly plug in 0 into the denominator. That won't work. Zeros in the denominators don't work. So how do we solve for this? Well, we're given a point, 2, 4, and the x-coordinate of this point is 2, which is important. So we'll keep this in mind using a green underline. Let's set up our limit. Let's set up our limit, though, now that we have all the information we need. Well, using the limit definition of derivative, our function is x squared. So our general function is f x squared. So we plug in x plus h into our function for x. So this originally was x squared, but we plugged in x plus h into x. And we subtracted by just our standard function, which is just x squared. And we put this all over h, correct? But we have our x value. Our x value is 2. So we can actually substitute in our x value here as 2. And 2 squared is also 4 over h. So what else can we do? Well, we can expand our squared term here. And expanding this gives us 2h plus, 4h plus h squared minus 4 over h. Now, look what happens. These 4's cancel out, so we just get as the limit as h approaches 0, 4h plus h squared over h. But looky here. The h at the denominator cancels out, and the h on this square cancels out too. So we get the limit as h approaches 0, 4 plus h. And all we can do is just plug in 0 here, and you get 4. Let's use green to circle. So the derivative at point 2, 4 is, so the derivative at point 2, 4 for our function x squared is equal to 4. Okay, this is technically not right notation because this derivative symbol at this function technically solves for the general formula for derivative, not the exact point of derivative. So ignore this. This is wrong. Math teachers, this is wrong notation. But people that are learning this, you get what I mean. So let me get the notation right this time. We're just solving for the limit definition of a derivative at x equals 1 for our function 1 over x. So the limit definition of derivative is, now keep in mind you have to memorize this because most calculus teachers won't give you a formula sheet with this in it, since you can work it out logically. And we just need to plug in for all of our values that are known. So our function is, so our formula is sort of like a guide. So our function is of x plus h. So what we do is replace our input with x plus h. And we subtract it by our function, which is just 1 over x over h. Now again, we can't just directly plug in 0, so let's ignore that. Now that we have this function and we know our x value, we can substitute in our x value. So as the limit approaches 0 for 1 over 1 plus h minus 1 over 1, actually, which is just 1. So we can just write this as 1 over h. So now what we can do is turn this 1 into 1 plus h over 1 plus h so that we can have the same denominator as the number we're subtracting from. So now that we have this, we have the limit as h approaches 0 for 1 over 1 plus h minus 1 plus h over 1 plus h over h. So now that we have this, let's combine the two fractions at the top together. And as a general side rule, most of the time you're literally just going to eventually have something that cancels. H will eventually cancel. And if h doesn't eventually cancel, you probably did something wrong. Or it's actually not possible for the derivative to be solved. That could be the case as well. But likely your teacher won't give you a limit definition of derivative problem without it being solvable. Okay? Now that we have this, as the limit approaches h, yes, writing the limit symbol is necessary every single time. These two ones cancel out. You get left off with h at the top over 1 plus h over h. Sorry, I made a little algebraic mistake. I have to distribute this minus. I have to distribute the minus, and h becomes negative here. So h is negative here. So when I subtract 1, so when I'm doing the math from the denominator, I need to put it in a parenthesis. And the minus actually distributes, so we get 1 minus 1 minus h. Made a mistake there. That one's a common one. And now that we have this, well, technically, dividing by something is multiplying by its reciprocal, but maybe if you already see this, you can actually cancel out these h values here. So the limit you get left off with is as the limit of h approaches 0 for negative 1 over 1 plus h. So now we can plug in 0 into here. If we plug in 0, we get left off with 1, negative 1 over 1, which is just equal to negative 1. So as you can tell, it's literally just algebraic manipulation. Solving for most limits is just algebraic manipulation, and then it's the same thing, just use algebra in order to solve for your problems. Now, hopefully your teacher doesn't give you extremely complicated formulas like 3x cubed plus 5x to the power of 4 minus 10 over x squared over the square root of x. Like, if they give you this for your limit, they're not even teaching you calculus. You're literally just doing algebra at that point. So hopefully you're going to get stuck with some simple problems since you're testing your calculus concepts, not your algebraic concepts. So that's why I'm giving you pretty simple problems to do in this video. But let's go ahead and solve for the limit here. Let's write down the limit definition derivative formula every single time to drill it into your heads. So we know our function is square root of x, correct? And our x value is 3. So let's go ahead and write down our formula specifically for this problem. This is the general formula, but we're writing down the formula specifically for the problem. So our function is the square root of x. Our input then becomes x plus h. So we replace x in our function with x plus h. Minus just your function of x. So technically we're plugging in x here, but x is the same. So we leave that with square root of x. Your function is just square root of x, so we can just substitute that into here. Over h. Now again, we can't plug in 0, so let's go ahead and algebraically manipulate this a little bit. So let's plug in the values for 3, since we're trying to solve for the limit at x equals 3. So as h approaches 0, for the square root of 3 plus h minus the square root of 3 over h. What we can do is multiply this by a conjugate. So 3 plus h plus square root of 3 over square root of 3 plus h plus square root of 3. So we're multiplying this by a conjugate so that the square roots can cancel out. So once we do that, we should get the limit as h approaches 0. So work on your algebra by multiplying these two functions together using FOIL. Once you do that, you should get 3 plus h minus square root of minus 3, over h times the square root of 3 plus h plus the square root of 3. Well, what happens is that the 3's cancel out here, and you get left off with the limit as h approaches 0 for h over h square root of 3 plus h plus square root of 3. Now, look what happens. Your h's again can cancel out. So this is what we're trying to go for. Denominator, get rid of the h. You don't want an h in the denominator. So that's the limit of h approaches 0 for 1 over 3 plus h plus the square root of, the square root of 3 plus h plus the square root of 3. So we can just plug in 0 directly now. When we plug in 0 directly, we get 1 over 2 times the square root of 3. I got that because you get square root of 3 plus square root of 3, which equals to 1 over 2 square root of 3. Now, you've been solving limits for, well, formulas. Well, for specific points, well, you can use a limit definition of derivative to solve for the general function of a derivative. So let's go ahead and show you an example for that. All right, let's solve for the general derivative function for x squared. Okay, I'm going to reorganize this since I kind of drew that too high. And let's use the proper notation this time. So what's a derivative of the general function x squared? Well, f of x is our function, x squared. And let's write our limits now. So x squared must be replaced with x plus h. So x plus h over, squared, plus our function, minus our function, x squared, over h. So what we did, again, is just replace x plus h with the x inside of the square, as this is our input for our function. Well, we can expand your x plus h squared to get x squared plus 2xh plus h squared minus x squared over h. Well, the x squareds cancel out since they subtract from each other. The limit now becomes something that is quite solvable over h. And we can actually factor out the h and cross out these terms. And we get left off with the limit as h approaches 0 for 2x plus h. But when we plug in 0 here, we just get left off with 2x. So the general formula for the derivative of x squared is 2x. And you'll soon learn the power rule in my next video. Link will be down in the description if you're curious. But the power rule supports this claim. All right? So the general derivative for x squared is equal to 2x. And remember, earlier in this video, the first problem we did, we solved for the derivative of x squared at x equals 2, or the point 2, 4 on your function. So let's go ahead and test this claim. At x equals 2, let's plug it into x squared. So let's go plug in 2 here, and we get 2 times 2, which is just 4. And if you go back in the video, we solve for the limit definition of derivative using x on x squared, and we plugged in for 2 in the limit definition of derivative. But what we can do is actually just solve for the general formula, and then we can find the derivative at any point. We don't have to just use the limit definition of derivative every single time. So this general function is actually quite useful, and I'll show you the rules for how to solve for these in the coming videos. But as always, if you have any questions, put it down in the comment section. If you found this video helpful, consider subscribing and like the video. Thanks for watching.